Welcome to the second part of the discussion of particle fluids. In the first part, I've introduced the general idea of particle-based fluid simulation. We have seen that a fluid volume is generally subdivided into particles. Then we compute accelerations at the fluid particles and we advect the particles. The accelerations at a fluid particle are described by the Navier-Stokes equation. So the Navier-Stokes equation is a differential equation that governs the velocity of a fluid particle. I've discussed that the accelerations in the Navier-Stokes equation account for various physical aspects, such as viscosity and incompressibility, and we have seen that these accelerations require spatial derivatives of certain particle quantities, for instance the Laplacian of the velocity or the gradient of the pressure. Now, one important question in a particle fluid solver is how to compute the spatial derivatives at the particles. There exist various options, and I've briefly discussed that we are going to use smooth particle hydrodynamics, or SPH. And now in this presentation, I'm going to focus on SPH. I'm going to discuss the general concept of SPH and its application in particle fluid simulation. So here we have the general organization of the introduction to particle fluids. Last time I've presented an overview of all relevant aspects in a fluid simulator. Here in this video I'm going to talk about SPH, and in the following videos I will be talking about neighbor search, boundary handling and various ways to compute the pressure field in a fluid. So here in this presentation we look into SPH. Here we see the context in which we apply SPH. We consider a particle-based fluid solver in which we use SPH for some of the computations. As a first step in a particle-based fluid solver, we always search particle neighbors within some distance. We have already discussed that this distance is equal to the support of the SPH kernel function and that we need the particle neighbors to compute SPH approximations. In the next step, we prepare the computation of the pressure acceleration that accounts for the incompressibility of a particle fluid. In order to detect whether a particle is compressed or not, we compute its density with the SPH concept as a sum over particle neighbors. Here J is the index of a particle neighbor and W is the SPH kernel function. If a particle is compressed, if its density is larger than the rest density of the simulated fluid, then we compute a positive pressure value, for instance with a state equation. Rho divided by Rho0 minus 1 characterizes a density deviation, and the multiplication with the stiffness constant K results in a pressure value. Then in the next step we compute the particle accelerations from the Navier-Stokes equation. We consider gravity and we compute the Laplacian of the velocity field to realize viscosity, and we compute the pressure gradient to preserve the rest density of the fluid particles. And here we use SPH to compute the spatial derivatives such as the Laplacian and the gradient. Finally, we apply the accelerations in the velocity update and we use the updated velocity to update the particle position. This is referred to as the advection step in a fluid solver. So in the implementation of the particle-based fluid solver on the previous slide, we have used the SPH concept for three computations. We have used it in the density computation, in the computation of the pressure gradient for the pressure acceleration, and also for the viscosity acceleration. We can see that the SPH approximations at a particle I are always sums over neighboring particles J. We also see that the SPH approximations use quantities that are available at the particles, and finally all SPH sums scale the contribution of a neighbor with a kernel function W or with a derivative of the kernel. The SPH concept basically corresponds to the reconstruction of a continuous function from a discretized version of this function that is given at discrete sample positions. Here in this illustration we have an unknown function shown in red, but we know some values of this function at selected positions indicated with blue lines. So each blue line is a known sample of an unknown function. In a fluid simulation, the function can be the density or the pressure or the velocity. And the sample positions are not 1D as in the illustration, but they are 2D or 3D. And the sample positions correspond to the representative positions of our particles. Now from signal processing, it is known that the unknown continuous function can be reconstructed from the samples by computing the convolution of the samples with a normalized Gaussian that is shown in green. So when we take the Gaussian function, slide it over all positions and compute a weighted average of the samples at each position where the weight is given by the Gaussian, then we get the reconstructed function shown in red. Now interestingly, the convolution can also be performed with derivatives of the Gaussian, where we would get a derivative of the function. So if the blue samples represent pressure values and we compute the convolution with the first derivative of the Gaussian, also shown in green in the illustration, then we get the first derivative of the pressure, which is the pressure gradient in 2D or 3D. That's the idea behind SPH. Another intuition for SPH is shown here, where we start with the fact that a function value a at a position x can be written as a convolution of the function a with a delta function. This follows from the fact that the delta function is 0 everywhere except at 0, and from the fact that the integral of the delta function over the entire domain is 1. Now we approximate the delta function with a kernel function that has a finite support of 2 times h, where h is the average particle distance or particle size. The kernel function w should approximate the delta function, and in particular it should converge to the delta function if the kernel support approaches 0. The integral actually shows a convolution, which means that we work with the reversed kernel function. As the kernel function is generally symmetric, this aspect is not too important in this case, but when we reconstruct the first derivative of a function with the gradient of the kernel function, then it is actually relevant. Now the convolution with a filter function can not only be used to reconstruct the function itself, but it can also be used to reconstruct its derivative. Let's say we have a function a and we would like to express the derivative of this function as a convolution with some filter function. This is, for instance, relevant if we would like to compute the gradient of the pressure field at a particle position. From the previous slides, we know that a of x can be written as a convolution of a and w at x. And now it turns out that this term can also be written as a convolution of the gradient of a with w, or as a convolution of a with the kernel gradient. These correspondences can be derived in different ways, but probably the most elegant way is to look at the Fourier transforms of all these terms. Here it turns out that the Fourier transforms are the same for all 3 forms of the convolution, so all 3 convolutions give the same result. This is actually highly relevant for practical reasons, as it allows to approximate the gradient of a function a by the computation of the convolution of the function a with the gradient of the kernel function. In a particle fluid, for instance, this concept allows us to compute the pressure gradient at a particle from the pressure field and the derivative of the kernel function. I do not go into details here, but the discussion of the first derivative is actually valid for all derivatives, as long as the respective derivative of the kernel function exists. Here we consider the second derivative of a quantity a, and it turns out that this derivative can be written as a convolution of the function a with the second derivative of the kernel function w. So the second derivative of the function a can be written as the integral of the function a multiplied with the second derivative of the kernel function w. In a particle fluid, this relation can, for instance, be used to approximate the Laplacian of the velocity in the viscosity acceleration just from the particle velocities and from the second derivative of the kernel function. Here we have a summary of the general properties that a kernel function should have. First of all, the integral of the kernel function should be equal to 1. So the integral should be normalized, which is also referred to as a unity condition. Then the kernel function should have a compact support. This means that the kernel function should be 0 for values that are larger than some user-defined value. In our setting, the kernel function is parameterized by the distance of 2 sample positions x and x primes, and samples that are farther away than, for instance, twice the sample size h should not contribute to an SPH sum. This means that we can discard neighbors that are too far away. Then the kernel should be symmetric. This actually accounts for the fact that the contribution of a sample at position x prime just depends on its distance to the position x. Next, the kernel function should be non-negative. One of the motivations for this constraint is the fact that we would like to avoid negative results in SPH sums, which would be non-physical. The next property states that the kernel function should converge to the delta function if the kernel support approaches 0. This is actually the case if the integral is normalized for arbitrary kernel supports. And then last but not least, the first and the second derivatives of the kernel function should exist. In an SPH fluid simulation, these derivatives might be required in the computation of the pressure gradient or in the computation of the Laplacian of the velocity field. So we know that a quantity A at position x can be approximated with the convolution of the function A with the kernel function W at position x. In the context of SPH, the respective integral is often written in a slightly different form, where we expand the integrand with the density at x prime. Now in the next step, we approximate the integral with a sum over discretized samples or particles xj. Each of these samples has a size v, a density ρ, and a mass m. In a particle simulation, the quantity A is only available at discretized particle positions. So the quantity A at an arbitrary position xi can be approximated as A times W times the volume v of a sample accumulated for all adjacent samples j. As the support of the kernel function is limited to 2h, we only consider neighboring particles j within the distance of 2h to the position xi. In the context of SPH, the volume of a particle is often written as mass divided by density, as indicated here. This form corresponds to the second integral in the first line of this slide. And finally, the kernel function is often written in a reduced form as wij, where I and j are the indices of the two considered particles. So once again, here we have an SPH sum that can be used to approximate a quantity A at a position xi from known values aj at particle positions xj with masses mj and densities ρj. We only consider particles j that are within the kernel support of position xi, and the contribution of particle j is weighted by the kernel function w, whose value depends on the distance between xi and particle j. We have seen that the derivative of a quantity A can be expressed as the convolution of a function A with the derivative of the kernel function w. In a particle setting, this means that the first derivative of a quantity A at position xi can be approximated with a sum over adjacent particles j, where we sum up the quantity A times the particle volume expressed as mass divided by density times the kernel gradient. Again, we see two possible notations for the kernel function. Now the same discussion holds for the second derivative, where we use the second derivative of the kernel function in the respective SPH sum. So we see that SPH allows us to compute spatial derivatives of a quantity A at arbitrary positions xi from irregularly sampled particles j. In terms of the SPH kernel function, there exist different options, and the selection of an appropriate kernel function, dependent on various factors, is still an ongoing research topic. Here in our course, we just discuss one prominent example, namely the so-called cubic spline kernel. The definition of the function is stated here for a support of 2h, and the parameter q is the normalized distance between the samples I and j. So if the distance between I and j is equal to h, then the parameter q is equal to 1. And we see that the kernel function depends on the dimensionality. So for 1D, 2D, and 3D, we have specific coefficients alpha that are required to normalize the integral of the kernel function. The cubic spline is close to a Gaussian, it is non-negative and symmetric, and its integral is 1. The support is compact and typically in a range from 2h to 5h. In our context, we very typically work with a support of 2h. The kernel support governs the number of neighbors that are considered in an SPH approximation. The support should not be smaller than 2h in order to work with a sufficient number of samples in SPH approximations, but on the other hand, larger supports negatively affect the performance. Here we have an illustration of the cubic spline kernel. We see its definition, and the graph shows 3 examples of the cubic spline for 3 different kernel supports h. We see that the function is symmetric, and we also see that its maximum value varies due to the normalization. The function is parameterized by the difference of 2 particle positions xj and xi, but due to the symmetry, the function actually depends on the distance between the 2 particles. In an SPH setting, the position xi is fixed and the position xj varies with the neighbors that are considered in an SPH sum. In SPH sums, we do not work with the kernel function itself, but due to the fact that we approximate a convolution, we actually use the reversed kernel function. So instead of using the difference xj minus xi, we use xi minus xj as the parameter of the kernel function. As the kernel function is symmetric, the function and its reversed form are actually the same. So here the distinction between the kernel and its reversed form would not be relevant. But the derivatives of the kernel function are not symmetric, so it's generally relevant to know that SPH sums are convolutions that work with the reversed form of the kernel function. In terms of the actual implementation, one efficient variant is shown here on the slide. Here on this slide, I'd like to discuss the first derivative of the cubic spline kernel. In general, the first derivative is often referred to as kernel gradient because in 2D or 3D simulations, the first derivative is a vector of the partial derivatives of the scalar kernel function with respect to all components of the position xj. Here we see the kernel gradient in a 3D setting. If the kernel function is parameterized with the normalized distance q, then the kernel gradient can also be written as the derivative of the kernel with respect to q times the gradient of q, which follows from the chain rule. So from the definition of the cubic spline, we know that q is the normalized distance between I and j, and we get the gradient of q by computing the spatial derivatives of q with respect to all components of the position xj. From the kernel definition, we can also compute the derivative of w with respect to q as shown here. Finally, the product of the gradient of q with the kernel derivative with respect to q gives the kernel gradient. Here we have an illustration of the 1D derivative of the cubic spline kernel for 3 different kernel supports. In contrast to the cubic spline, its derivative is not symmetric but antisymmetric. The function is parameterized with the difference of 2 positions xj and xi, where the position xi is typically fixed in an SPH approximation, while the position xj varies with the neighbors that are considered in the SPH sum. Now, here in case of the first derivative, it makes a difference whether we work with the original function or with its reversed form. Here on the left-hand side, we see the kernel derivative in its original form. Again, we typically use the kernel derivative to approximate a derivative at a fixed position xi, and we therefore use neighboring particles with varying positions xj. Now we remember that SPH computes a convolution of A with the kernel gradient to approximate the first derivative of A. And in this convolution, the reversed form of the kernel derivative is used. So in an SPH sum, we parameterize the kernel gradient with xi minus xj instead of xj minus xi. This actually implements the usage of the reversed kernel gradient. Here we also see an alternative reduced notation of the SPH sum, and we also see the general definition of a convolution where we have the reversed form of the filter function g in the integrand. This is the reason for using the reversed kernel function and the reversed kernel derivatives in SPH sums. Finally, on the right-hand side, we see an illustration of the reversed kernel derivative, and we also get an idea how to use this function in an SPH approximation. When we know a quantity A at some selected particle positions xj, indicated by the blue lines, then we can compute the derivative of A at a position xi by multiplying the quantity A at position xj with the kernel derivative at xi minus xj, accumulated over all particles j within the kernel support. And as the kernel derivative is antisymmetric, the reversed kernel derivative is equal to the negative of the kernel derivative. Here on this slide we have one efficient variant to implement the derivative of the cubic spline kernel. Similar as for the cubic spline itself, it's rather efficient to compute two polynomials t1 and t2 within the range from 0 to 1 or 0 to 2, and to combine these polynomials for the final value. In addition to the first derivative, we are also sometimes interested in SPH approximations of a second derivative, where we need the second derivative of the kernel function. The second derivative of the scalar kernel function is a scalar value that is equal to the sum of the second partial derivatives of the kernel function with respect to all components of the sample position xj. Similar as for the first derivative, the second derivative can be written in terms of the parameter q, which is the normalized distance between two samples I and j. And then we have the respective terms. We have q, we have the squared gradient of q, and we see the Laplacian of q. Finally, we have the first and the second derivative of the kernel function with respect to q. And combining these terms in the indicated way gives the second derivative of the kernel function. Here on this slide I'd like to indicate how SPH kernel functions are typically designed, and as an example we look at the 1D version of the cubic spline. In general, we define the shape of the kernel function, which should be non-negative, symmetric, and close to a Gaussian. And the function should have a compact support. So we define a shape that is denoted with W tilde here on this slide. And then as a final step, we estimate the coefficient alpha to fulfill the constraint that the integral of the kernel should be 1. The constraint is stated here, and we also see how to estimate the respective integral in this 1D setting. Finally, we get a scaling coefficient alpha that depends on the kernel support. It's intuitively clear that the scaling coefficient converges to infinity if the kernel support approaches 0. On the previous slide, we have discussed the derivation of the normalization coefficient for the cubic spline in the 1D case. Now here on this slide we see the derivations for the coefficients in the 2D and in the 3D setting. For the 2D setting, we compute the integral of the non-normalized kernel function W tilde over the area of a circle with radius 2h, which is the support of the function. So for all positions outside this circle, W tilde is 0. We see the result of the integral, and 1 divided by this value gives the normalization coefficient alpha for the 2D cubic spline. The same steps are applied in the 3D case, where we integrate the non-normalized kernel function over the volume of a sphere with radius 2h. Again, we see the result of the respective integral, and 1 divided by the integral gives the normalization coefficient. So on this slide and on the previous slide, we have derived the normalization coefficients for the cubic spline kernel in 1D, 2D, and 3D. And we keep in mind that the normalization coefficient depends on the shape of the kernel and also on the dimensionality of our setting. In terms of the concept behind SPH, namely the reconstruction of functions and derivatives from discrete samples, there exist standard SPH expressions for the derivatives. We know that we would like to realize the convolution of the samples with a kernel function or with a derivative of this kernel function, and we can approximate this convolution at a sample I with the stated sums over nearby samples j. Now these sums are theoretically the best choices for the derivatives, but in practice people often prefer alternative formulations. This is typically due to the fact that the samples in an SPH simulation are not always perfectly distributed. And in such a case, the actual volume of a sample does not exactly correspond to the volume that is used in the SPH sum. then the approximation is less accurate. Additionally, in some cases, the neighborhood of a particle is not completely sampled with particles, which also leads to errors. For instance, if a particle in an SPH fluid is at the surface of the fluid, then its neighborhood is incomplete and the SPH approximations are erroneous. In order to address these issues, there exist alternative SPH approximations. For a perfect particle distribution, the alternative formulations correspond to the original forms, but for erroneous distributions, they enforce certain properties of the computed derivatives. For instance, if we compute forces from the pressure gradient, these forces should always preserve the linear and the angular momentum of the particle system. And this requirement should be fulfilled independent from the quality of the particle distribution. Or the divergence of the velocity should be zero for a constant velocity field, also independent from the sampling quality. And that's why alternative SPH approximations have been proposed for specific purposes. The first alternative formulation is the so-called anti-symmetric form that is often used to approximate the gradient of the pressure field. The SPH approximation for the respective pressure acceleration is shown here, and the main motivation for introducing this form is the fact that the corresponding particle forces preserve the linear and the angular momentum of a particle system. So in particular, the sum of all pressure forces is zero, and the pressure forces do not cause any global torque. One way to derive this formulation is to start with the gradient of a quantity A divided by the density ρ. We rewrite this term in order to get another term that contains the gradient of A. Now the equation can be solved for the gradient of A. Now instead of using SPH for the approximation of the gradient of A, we use SPH for the approximation of the gradient of A divided by ρ, and we use SPH for the approximation of the gradient of ρ. The two resulting SPH sums are simplified, and we get the final SPH formulation for the gradient of A. And now it can be shown that the resulting forces preserve the linear and the angular momentum for arbitrary samplings. This is indicated here for a system that only consists of two particles I and j. We see that the pressure force Fp at particle I is always equal to the negative of the pressure force Fp at particle j. And this relation holds for arbitrary density and pressure values at the particles, for arbitrary masses mi and mj, and also for arbitrary positions of the particles, as the kernel gradient wij is always equal to the negative of the kernel gradient wji. Another alternative SPH approximation for the first derivative is the so-called symmetric form that is often used for the divergence of the velocity. This formulation is motivated by the fact that it is zero if the velocities at all particles are the same. And this property is always fulfilled independent from the particle distribution. The derivation of the symmetric form is pretty much the same as for the anti-symmetric form. We just start with another relation for the gradient of a quantity A. We do not start with the gradient of A divided by ρ, but we start with the gradient of A times ρ. We apply the product rule and solve the resulting equation for the gradient of A. Then we apply SPH approximations to the gradient of ρ times A and to the gradient of ρ. And finally, the two SPH sums are simplified, and we get the symmetric SPH form of the first derivative of A. This variant is often used for the SPH approximation of the velocity divergence, where we get zero divergence for a constant velocity field independent from the sampling quality. In addition to the first derivative, there also exist alternative SPH approximations for the second derivative. Here the main motivation is to avoid the usage of the second kernel derivative, which is considered to be sensitive to the particle distribution. Also, the second kernel derivative is typically not sufficiently sampled for smaller kernel supports. That's why second derivatives are typically approximated by combining the first derivative with a finite difference approximation. The formulation works with scalar quantities A and also with vector valued quantities. And in practice, this formulation is often used to approximate the Laplacian of the velocity field in the computation of the viscosity acceleration. Please note that the term 0.01 times h squared is just a small offset to avoid a division by zero in the special case where two particles I and j would be at the same position, which should actually not really happen in a simulation. So in summary, there exist various forms for the SPH approximations of derivatives. On one hand, there exist the original forms that are motivated by the original SPH idea, and on the other hand, there exist alternative expressions with specific properties that are always fulfilled independent from the quality of the particle sampling. So for the pressure gradient, we prefer an approximation that always preserves the linear and the angular momentum of a particle system. For the viscosity, we prefer a form that does not use the second kernel derivative, and for the velocity divergence, we take an SPH approximation that always results in zero for a constant velocity field. So the stated alternatives are considered to be more robust in case of particle disorder. Now in the following, I'd like to discuss some properties of the kernel and of the kernel gradient, and I also try to improve the intuition of the usage of these functions in SPH approximations. Here we start with some properties. If the particle distribution is perfect, then the density of particle I is equal to the sum of the masses of the neighbors j weighted with the kernel value wij. In our setting, all particles have the same size, so all masses are equal, and we can write the mass of particle I in front of the sum. In addition to this SPH approximation for the density, we also know that the density is equal to mass divided by volume. And these two relations lead to the property that the sum of the kernel values over the neighbors j is equal to 1 divided by the volume of particle I. This is also related to the fact that the integral of the kernel is equal to 1. As the kernel function is symmetric, the kernel gradient is antisymmetric. So the kernel gradient for the particles ij is the negative of the kernel gradient for the particle pair ji. This can also be seen from the form of the kernel derivative that contains the difference xi minus xj. And we define that the kernel gradient for the particle pair ii is equal to 0. From these properties, it follows that the sum of the kernel gradient over all neighbors gives 0 in case of a perfect sampling. Another important property for the kernel gradient is that the sum of the outer products of xi minus xj with the kernel gradient is equal to minus 1 divided by v times the identity matrix. All these stated properties can be used for different purposes. For instance, they can be used to analyze the particle distribution and also to correct SPH approximations in case of particle disorder. Or they can be used for test purposes in SPH implementations. Now here we have a very simple 1D illustration of the cubic spline kernel in an SPH setting. We see the definition of the 1D cubic spline and we see the function together with 5 1D particles that sample some quantity. We assume a perfect particle distribution, so the distance between all samples is equal to h, and the kernel has a support of 2 times h. Now we compute the SPH sum of the kernel at one of the samples. So in the SPH sum, we have one sample with distance 0, and we see the respective kernel value. Then we have two samples at a distance of h, which corresponds to a distance of 1 in terms of the parameter q. And finally, we have two samples at a distance of 2h corresponding to 2 in terms of q. If we compute the SPH sum of these kernel values, then we get 1 divided by h, where h is the size of a 1D particle in our setting. So this is a 1D illustration of the property that the kernel sum is equal to 1 divided by the particle volume. Here we have the discussion of the same property in 2D. We see the definition of the 2D cubic spline, and we see perfectly distributed 2D samples, where each sample represents an area of h squared. Again, we would like to compute the kernel sum over all neighbors of the sample in the middle. In the SPH sum, we have one sample with a distance of 0, we have 4 samples at a distance of h, and we have 4 samples at a distance of h times the square root of 2. In terms of the kernel parameter q, these distances correspond to 0, 1, and square root of 2, and we see the respective kernel values. Now if we sum up all kernel values for all neighbors, then we get 1 divided by h squared, where h squared is the particle size. So again, the sum of the kernel values is equal to 1 divided by the particle size. Now here I'd like to illustrate how the discussed kernel property is used in an SPH fluid simulation. It is used to approximate the density ρ at a particle, but actually it's not really used to reconstruct the density, but instead it detects an erroneous sampling. If the particle sampling is perfect, we have the following case. The distance between all samples is equal to h, and as discussed on the previous slide, the sum of the respective kernel values gives 1 divided by the particle size. If we multiply this term with the particle mass, we get the particle density ρ. Now here in this 1D illustration, the desired rest volume V0 of a particle is equal to h, so for a perfect sampling the particle density ρi is equal to the desired rest density ρ0. Now in fluid simulations, this computation is used to detect erroneous particle densities or volumes. If for instance at some time t the particles would be compressed, then the actual distance ht at this time point t between the particles would be smaller than the desired rest distance h. So the distances between particle I and its neighbors would be smaller, and we would get larger kernel values. This means that the kernel sum would be larger than 1 divided by the rest volume V0, and we would get a particle density ρi that is larger than the rest density ρ0. Now on this slide I'd like to illustrate the SPH computation of a first derivative in 1D. We see the first derivative of the cubic spline kernel in 1D, and in the illustration we see some blue samples at positions x that represent some pressure values p. We see that the distances between the particles are equal to h, and we see that the differences between adjacent pressure samples is also h. So the first derivative of the pressure function is obviously 1. Now we would like to approximate the first derivative of the pressure function with SPH at position xi. And therefore we consider the original form of the SPH derivative, where we compute the sum of the pressure values multiplied with the reversed kernel gradient over all neighbors. So for all neighbors of xi, we evaluate the reversed kernel gradient illustrated with the yellow points. This value is multiplied with the pressure value stored at that sample, and then we accumulate all these products for all neighbors. In this ideal setting, the kernel gradient is 0 for 3 of the neighbors, and finally only 2 samples actually contribute to the result. We see that we get the expected result, and we also see that the final term actually corresponds to a central difference in this special case. The same is actually also true in 2D or 3D. If you have a perfect and regular grid-aligned sampling, and if the kernel support is equal to 2h, then the SPH approximation of a gradient is equal to a central difference approximation. Now on the following 2 slides I'd like to illustrate the property that the sum of the outer product of distances to neighbors with the kernel gradient is equal to -1 divided by the particle size times the identity matrix. We look at a perfectly sampled 2D setting, we see the definition of the cubic spline kernel gradient, and we see some values of the kernel gradient for selected particle pairs. Here we have the selected kernel gradients from the previous slide, and we also see how to compute the outer products for all particle pairs. We distinguish the computation of the diagonal values, where we get -1 divided by the particle size, and the computation of the off-diagonal values, where we get 0. Again, this property is particularly useful for test purposes. Now here on this last slide, I'd like to discuss another practically relevant property of the kernel gradient, namely the fact that sums over kernel gradients can not only be used to approximate the derivative of some quantity, but they can also be used to detect irregular samplings. In particular, sums over kernel gradients result in vectors that point from low to high sample concentrations. Here we have the gradient of the cubic spline kernel, and we have an example with two 3D particles with a distance of h. We see that the kernel gradients at the particles point towards each other. A practical application of this property is actually the estimation of surface normals. Here we have some particles, and if we compute the sum of the kernel gradients at any of the surface particles, then we get the negative of the surface normal at that position. As the kernel gradient points from low to high sample concentrations, the negative of the kernel gradient points away from the particles. If we compute the sum of the kernel gradients inside a particle system, then we get 0. This has been discussed as one of the properties of the kernel gradient. So from the sum of the kernel gradients over the neighbors, we can actually detect whether the neighborhood is properly sampled with particles or whether there are missing samples. That's it about the introduction to SPH. Thanks for your attention.